So my talk will be a bit more general than the former ones. And I would like to discuss, do living fossil fishes exist, and does it matter? So the concept of living fossils, as you know, has been proposed by Charles Darwin in The Origin of Species in 1859. And it defines some organisms that may almost be called living fossils. And in his definition, there are several important features. And these organisms lived in an environment in which new forms will have been more slowly formed and old forms more slowly exterminated. This is one aspect of the definition. Another one is that they are remnant of a once preponderant order, or they connect to a certain extinct orders now widely separated. And finally, they usually lived in confined areas. So for Charles Darwin's living fossils were mostly freshwater organisms. And as example, he mentioned several Guinot fishes, and also Ornithorhynchus and Lepidosiren, so the lungfish. So we may think that living fossils is the word mostly used in popular science, but actually not. And we have a lot of papers with living fossils in the title. For instance, here in Science, for the cycads, modern survivors of previously more diverse lineage. So this is one aspect of the definition. Here for the ginkgos, it's phylogenetically isolated relectual distribution. Okay, here for a tick, closest living relative to the ancestral tick lineage. And here for the famous Nautilus, oldest group of the clade. And of course, for fishes, we have also an example of so-called living fossils, with, for instance, this Protangia, described some years ago, which is on an independent evolutionary history, and the Australian lungfish, Neoceratodus here, the oldest surviving vertebrate genus. And here, the most famous one, probably, Coelacanth, with this title, A Living Fossil in the Genome of a Living Fossil. It's a living fossils because it's the only vestige of a deep evolutionary lineages, and so on. So this is a term which is widely used in scientific literature. So now I would like to focus a little bit more on this example here, the Coelacanth, Latimeria. So this paper has been published this year by Cavin and Laurenti, and the title is Why Coelacanth Are Not Living Fossils. And in this paper, they discussed mostly molecular studies, but they also discuss a little bit morphological data, and I would like to focus a little bit on this part of their work. So here they provided this cladogram of Actinistia, of Coelacanth, and they mentioned that this figure here illustrates the morphological diversity of Coelacanth, and I'm not convinced with this figure. Of course, here we have some Devonian taxa, which are quite different from the recent one, but otherwise it's quite stable, I think. And they also mentioned some differences in the skull morphology, with the most closely relative in the Cretaceous, or one of the most closely relative, which is Macropoma, and they mentioned some differences in the shape of the ungulate, or shape of the rostrum, or shape of the skull roof, anterior part of the skull roof. For me, it's not very big differences. And here there are some other differences in the number of vertebrae, or the space between vertebrae, the size, the body size. Once again, not so important for me. And what is missing, I think, in this study is the time dimension. They did not include this important aspect in the study. So what we did here, we included the phylogeny, the cladogram from Cavin and Laurenti into a time scale, with Latimeria here and Miguashaya here. And we did the same for 3 other vertebrate clades. And then, this is a very simple thing. We just look at the next node and counted the number of synapomorphy which support these nodes. And we looked in different papers to list this synapomorphy. And we did that for each node based on this cladogram here for Coelacanth. This is the next node. And then we just did the addition of all these synapomorphies, and we divided by the number of million years. And here you have the number of synapomorphy per million years for these four clades. And here this is the hummingbirds with more than 0.2 synapomorphy per million years. And here it's the actinistian with about 10 times less. And sharks and ray fin fishes are in between. So actually, I think that based on this comparison, we can think that we can say that coelacanth correspond to organisms living in an environment in which new forms will have been more slowly formed and old form more slowly exterminated. So this is one part of the definition. And if we look now at the diversity of three fish clades with the ray fin fishes here, this is not the observed number of family, but the number of observed family plus ghost lineages, with almost 400 families today. This is the curve for sharks, with more than 50 families today. And this is the number of genera, not families, for actinistian. And if we have a closer look at this diversity for actinistia, we see that there is a peak of post-Palaeozoic diversity, I would say. We have a peak of diversity in the early Triassic, then it's almost constant, and then we have a drop of diversity until the present. So this aspect also, the taxic diversity, is something important to define coelacanth, and we can say that they are remnant of once preponderant order. So, okay, it was not preponderant, but it was much more diverse. So now it's another example of a fish which is sometimes called a living fossil, the Australian lungfish, Neoceratodus. So 10 years ago, we discovered this specimen in northeastern Thailand in the early Cretaceous. It's the skull and the jaw of a lungfish. And we did a phylogenetic analysis with this new species. And most of the former analysis or phylogenetic analysis of post-Paleozoic lungfishes showed sister group relationships between the African Neoceratodus and the South American Lepidosiren or African Protopteris. So the living lineages are sister group in all these studies. And with this, the inclusion of these new species and also with the new definition of characters supporting the analysis, we provided this phylogeny in which Neoceratodus is far away from Protopteris, separated by all these Triassic and Jurassic taxa. So the split between the Neoceratodus lineage and the Protopteris lineage is now much, much older based on this phylogeny. And this is the phylogeny of fish Sarcopterygian. And here, this is the former split in the early Cretaceous. And now, with this new phylogeny, the split is here, more or less at the Permo-Triassic boundary. And ecologists have tried to define evolutionary distinctness. And one method was defined by Isaac and collaborators in 2007. And this method suggests that you can measure this evolutionary distinctness by counting, by doing a kind of calculation. This calculation is based on the number of million years for each branch divided by the number of terminal taxa. So you see here you have 370 million years divided by 2. And then you add here this branch here with 400 divided by 1. And based on the former phylogeny, the Australian lungfish had this value here, and now with the new phylogeny, the evolutionary distinctness of lungfishes, of Australian lungfishes, is 277, which means that the inclusion of a fossil in phylogeny can change the evolutionary originality of a living organism. And this corresponds in part to the definition of living fossils made by Darwin. Living fossils, like fossils, connect to a certain extent order now widely separated in the natural scale. Okay, the third example is this shark here, the Cladonautomorph. And this is general phylogeny of Chondrichthyon with the crown group here. And Cladonautomorph are stem chondrichthyon here supposedly became extinct at the Permo-Triassic boundary. And these are a few examples of falcatid, this Palaeozoic cladodontomorph. So my co-author, Guillaume Guinot, described shark assemblages based on more than 10,000 isolated teeth from this locality here, located in southern France, in the Gard department, and which is Valanginian in age. And most of the fauna are quite usual for early Cretaceous, but among these 10,000 teeth, 6 were very unusual. And some of them are presented here, and actually they belong to cladodontomorph. So one can be referred to the falcatid here, and others could be referred to a ctenocotiform indet or cladodontomorph indet. So we have here evidence of surviving cladodontomorph in the early Cretaceous. And something important to say also is that this environment corresponds to a rather deep environment in the early Cretaceous. So we have a pattern here quite similar to what is observed in Coelacanth today. So the group who are living in different environments in the Palaeozoic, then we have no more fossils, and we find a new specimen in deep sea environment. But here the gap in the fossil record is much longer than for Coelacanth. Yes. So this corresponds also to one part of the definition of living fossils made by Charles Darwin. So they have endured to the present day or to the Cretaceous from having inhabited confined area and from having thus been exposed to less severe competition. So as a conclusion, living fossils is yes, it's a semi-scientific term because of course a fossil cannot be living, we know that, yes. But which characterize a range of genuine biological phenomena and which are actually often strongly correlated. And I think that yes, we can say that living fossil fish exist with examples showing the different aspects of the definition given by Darwin. And does it matter? I think yes, it matters. Also, it is very imperfect because it encompasses organisms with peculiar evolutionary histories. And the best conclusion, I think, is from Charles Darwin himself, because in his conclusion, he mentioned for the second time the word living fossils. And he wrote that species are a group of species which are called aberrant and which may be fancifully be called living fossils will aid us in forming a picture of the ancient form of life. And this is exactly what I tried to say here in this talk. Thank you.